Hi, welcome to Recitation 10, our first online recitation. So today we're going to be talking about undecidability and recognizability. And before we get into it, I just want to do a quick review. So an undecidable language is a language where you can definitely come up with the answer yes for inputs in the language and no for inputs not in the language. This is equivalent to saying that there exists a Turing machine that will accept inputs in the language and reject inputs not in the language. And accept and reject means that the Turing machine will halt. So you're guaranteed the Turing machine will not loop on any input. An undecidable language is one where you can't handle the accept and or the reject case. So there does not exist a Turing machine that is guaranteed to accept inputs in the language and reject inputs not in the language. So today we're going to be proving that certain languages are undecidable, and we're going to do this using a mapping reduction. So just to review, a mapping reduction is like a function that takes in an input in one language and outputs, or takes in an input and outputs an output, and if the input is in the initial language, then the output has to be in the output language. And if the input is not in the initial language, then the output must not be in the output language. So the reason why this works in proving that languages are undecidable is that if you start with an undecidable language, you're proving that language B here, the second language, is at least as hard of a problem as language A. So if A is undecidable, B must be undecidable, because if you can't solve language A, or if you can't decide language A, then you can't decide language B either. So in terms of problem 1, which Aditi will go over in a second, the initial language is ATM, which we know is undecidable, and we're proving that right 1 is undecidable as well. So we're going to define a mapping function that takes in inputs, and if the input is an element of ATM, then we must output a machine that's in right 1. And if the input is not in ATM, we must output a machine that's not in right 1. And just to review, ATM is the pair of M, X, where M accepts X. So M is a Turing machine and X is some input. And generally, ATM is actually really useful in undecidability proofs. They're like kind of formulaic, and you'll see why in a second.
This is the first problem from Recitation 10, where we're going to show that the language right 1 is undecidable. So the language right 1 takes in input T, where T is a Turing machine that writes a 1 during some computation. And we're going to show that the language right 1 is undecidable by giving a mapping reduction from ATM to right 1. So what that means is we're going to show that if right 1 were decidable, then we would also be able to decide ATM too. But we know that that's not possible because we've already proved that ATM is an undecidable problem. If right 1 were decidable, our algorithm to be able to also decide ATM would look like this. So our algorithm F would be to take in, and it would construct a Turing machine R. And we want this machine to be in right 1 if and only if MX is in ATM and vice versa. So R is going to take in input Y, and it's just going to ignore that input completely, and it's just going to run M on X. And if M accepts X, then R would just write a 1 and accept Y. And it only does this if M accepts X. If M rejects X, then it doesn't write anything to the tape. So then the second step of the algorithm would be to just return that machine that we just created. But there is one problem with this. So what if M rejected X, but it wrote a 1 to the tape during the computation? The thing to consider here is that because R was simulating M on X, it's using the same tape. So if M had written a 1 during the computation, then our TMR would be in right 1, even though MX was not an ATM. So this wouldn't be a good reduction, so we need to add some extra steps. So the revised algorithm is to convert M's input alphabet so that every symbol A in that alphabet is replaced by A hat, including its transition functions. And we're also going to convert our input string so that each symbol A and X is replaced by A hat. So the reason we do this is because we want to make sure that when we're simulating M on X, we don't want to actually write a 1 to the tape because then R would be in right 1, even though R didn't actually write a 1 to the tape because there was already a 1 on the tape from the other computation. So when we replace the symbols, we're making sure that there's only a 1 on the tape if M had accepted X, because R is just going to run the converted machine M on the converted X. So this is our proof that M accepts X if and only if R writes a 1 on its tape. So we called M hat R in our explanation. So MX is in ATM, which means that M accepts X based on the definition of the language. And if M accepts X, then M hat writes a 1. And M hat, which means that M hat is in right 1. And the other important thing is if MX is not an ATM, then M does not accept X, and M hat never writes a 1, because we guaranteed that by switching or doing the conversion to the alphabet, because there would only be a 1 on the tape if M hat had written 1, not if there was already a 1 on the tape from simulating M on X, which means that M hat is not in right 1. So that's our reduction proof. So the second problem is an extension of the first problem, and it's asking how we can modify the previous proof for the language right 1 to prove that right A is undecidable for any symbol A that we want. So we're going to do our proof the same way, where we just assume that the first step is to always just assume that right A is decidable. And now instead of writing in a 1 at the end of the accepting computation, we're just going to write an A instead. So it's pretty much the same proof. And let's say our symbol that we want to check for is right A hat. But it doesn't matter, because even if A hat were written by M, then the new version would write A double hat. So no matter what, we're converting the alphabet so that the original symbol isn't going to be written by M.
All right, now on to problem 3. So now we're dealing with a similar language called Write01, and this is the set of Turing machines that writes both a 0 and a 1 during some computation. So it's basically just like Write1, except in order for a machine to be in the language, it has to write a 0 and a 1 in whatever order. You could solve this problem similar to how you did problems 1 and 2 by reducing from ATM, but that's boring, and you could do something more clever by reducing from another language that intuitively fits your new language a little bit better. So we're going to follow the same strategy as before by constructing a mapping reduction that takes in an input of write1, and we're going to construct a new machine that is in the new language if and only if the old machine M was in write1. And then we return the new machine that we just constructed. And in the context of this problem, this is saying that the new machine, let's call it 01, is only going to print 0 and 1 if and only if, I'm going to do this, if and only if M printed 1. So now you can pause and take a few minutes to try the problem on your own, and when you're done, you can come back to this video and see the solution. So the first line of our proof is going to be pretty much the same as before. We're just going to say that we're constructing a new machine that follows like the mapping reduction constraints. And now we can start constructing the machine. So the idea here is that we want M0 to print both a 0 and a 1. However, we know that if M prints a 1, all we have to do is also have M0 print a 0 at some point, and then it satisfies the constraint to be in right 0, 1. So what we're going to do is make it so that M0 always prints a 0 at the very beginning, and then gets rid of it so it doesn't mess with the rest of the computation. Then immediately after that, we're just going to simulate M as usual. And at the end, return the new machine. So to reiterate, if the original M writes a 1, then the new machine you just constructed is guaranteed to write a 0 and then a 1, which makes it in right 0, 1. And if the original machine never writes a 1, then the new machine also never writes a 1, and it can't be in right 0, 1. Thus, we have satisfied both the in-to-in case and the out-to-out case for a mapping reduction. Alright, now on to problem 4. So before we start, I'm going to revisit the definitions from earlier, and I have added a new definition for Turing recognizable. Now, recognizable is very similar to decidable, except you can only deal with the except case. This means that if a language is recognizable, then there must exist a Turing machine that can accept inputs in the language, and it will not accept inputs not in the language. The Turing machine will either reject or loop on inputs not in the language. Now, problem 4 says, suppose you have two recognizable languages. You can construct the machine to recognize the union by running the machines for the two languages on the input in tandem. And then if at any point either of the machines accept, then you accept overall. The reason why you can't do the same thing as with two decidable languages, where you run the first machine on the input and then run the second machine on the input if the first one didn't accept, is because the languages A and B are only recognizable. They're not guaranteed to terminate. So if the input is not in language A, but it is in language B, and the machine for language A loops on the input, then we can't just run it first and then wait for it to halt, because it'll never halt. So we have to do this thing where we alternate between instructions, where you keep track of the state of the tape and what symbol you're on and which state you're in for each of the two recognizers. And this is also called time sharing. So now the question asks you to show this also for A star. Here's a simple example of an A and corresponding A star, and of course if the language is regular, then it must be decidable and it must be recognizable. Take a second to pause and look at the provided example and try to come up with your own answer before we continue on to the solutions. Okay, so let's get into it. The first thing we need to do is deal with the empty string case. So except if length is 0. Then we're just going to use that fun little word timeshare and split the string into, at most, the length of x non-empty substrings, as in the substrings have minimum length of 1, and timeshare across each of the substrings for each partition. And if on any partition, if the original recognizer accepts every substring, then we accept overall. So if x is in A star, then it's either an empty string or it can be split into some partition of substrings where the recognizer accepts on each substring, and it'll never get stuck in a loop because we're time sharing across all possible partitions. Thus, M will accept the x overall. If x is not an A star, then there does not exist some partition where each substring is accepted by the recognizer, and M will never accept x. Alright, that's all. Thanks for watching.